In this lesson, we're going to be studying polynomials. I might suggest that you pause the video and read through all this information right here to gain an understanding of these different terms. Then after you read through all of this information, just self-assess. Based on what you read here, can you extract the necessary information to answer all these blanks for example 1? All right, so a term is either a single number, a constant, a variable, which is a letter, or a combination of both, meaning I'm multiplying. So looking down here at example 1, we'll go through each of these terms by using example 1. So a term is a single number or a variable or a combination of both. I like to say that terms are what you add or subtract, and that's kind of a visual for me. So let's look at example 1. Terms are what you add or subtract. So I see a plus sign, a minus sign, and a plus sign. So 7 is the first term, 2x cubed is the second term, x is the third term, and x to the fourth is your fourth term. So how many terms do I have in this polynomial? I have 4 terms. This is asking what are those specific terms? Well, 7, comma, 2x cubed, comma. I'm going to go ahead and put negative x. I use the subtraction sign as a negative, comma, 8x to the fourth. Okay, is this a polynomial? Yes or no? Well, that requires us to go back up here and look at the definition of a polynomial. A polynomial is a single term or the sum difference of 2 or more terms. So far we're okay. We have 4 terms, that's allowed, where they contain variables, letters, with exponents that are whole numbers and coefficients, numbers in front of a group of letters that are real numbers, not imaginary, no i's. All right, so that's a lot. So you might have to keep referring back to that as you study each and every term of this example. So is this a polynomial? Well, 7 is a single term and it's a number, and that number is a real number. So we're good there. I might look over here at the individual terms. 2x cubed. Okay, I have to look at the variable x and I have to study its exponent. That 3 is a whole number. It's not negative, it's not a fraction. And the coefficient of this term, 2x cubed, is 2. So the coefficient has to be a real number. So yeah, 2 is a real number. Right, when I look at this third term right here, I want to look at the variable and I want to inspect the exponent. Well, the understood exponent is 1, and 1 is a whole number, so we're good there. The next thing to inspect is the coefficient, the number in front of a variable or a group of variable factors. Well, this number in front of x, you can think of it as -1. There is an understood 1 here. We just don't, common practice, show it. So far, this term satisfies the description of a polynomial. And then the last term here, looking at the variable, that exponent is a whole number. The coefficient of 8 in this term is a real number. So polynomial, yes. Why or why not? And I'm just going to say C above. We already went through that, so that's good enough. All right, so what's the degree of our example? Well, let me go back up here and look and see what the degree says. The degree of a polynomial is the highest degree of all the terms, the highest exponent. All right, so I'm going to look at these 4 terms right here. I'm going to look at the exponents I have. I have 3, 1, and 4. 4 is the highest exponent, so it's telling me that the degree is the highest exponent. It is that number. So the degree of this polynomial is 4. All right, it's asking me what's the leading coefficient of this example. Oh, I got to figure out what leading coefficient is. So I see leading coefficient here. It says it's the term that determines the degree also carries the leading coefficient. The term that determines the degree, so that would be 8x to the fourth, also carries the leading coefficient. Coefficients are numbers that are in front of variable factors. So when I look at this right here, if it's asking me what's the leading coefficient, the leading coefficient is 8. And I'm going to add something here. If you were asked to find the leading term, the lead term. This is going to come up later in a different section, and we're going to need to know this information on a polynomial. So the leading coefficient refers to a number that's a real number, so that's just 8. Well, what's the leading term? Well, the lead term is the whole entire term that has the highest exponent. So the lead term would be 8x to the 4th. So make sure you kind of understand the difference between the word coefficient, just number, term means the whole group. It says rewrite this expression in standard form. Okay, what's standard form? The terms, these 4 terms of polynomial are written in descending order of the powers of the variables. So from greatest to least, we look at the exponents and we rearrange these 4 terms. So the highest exponent is 4, so we would write the polynomial starting with 8x to the 4th to put it in standard form. Looks like we have a plus 2x cubed. Next highest exponent on a variable would be this minus x. I don't need the understood 1 coefficient nor the exponent. And the last term, don't forget, is plus 7. All right, let's look at another example, kind of go through it more quickly. If you're comfortable with all of this, great. Well, then after we get this written down here, just think about how you would answer all these questions for our additional example, and then you can turn the video back on and see how you did. I'm going to make that an 8. Negative 3x to the 8th. Minus 6x squared plus 2x minus 3. So the first question for me would be, is this a polynomial? Yes, it is, because by inspection, the first thing my eyes land on are all the exponents of any variable. So 8, 2, the understood exponent of 1, 8, 2, and 1 are all whole numbers. Good to go. Then I look at any coefficients to make sure that they are, or constants, to make sure that they are real numbers. So the coefficient in this term right here would be negative 3. The coefficient here would be negative 6. The coefficient here would be 2. This is a constant because it doesn't have a variable with it, and this constant also is a real number. So to answer the question, yes, this is a polynomial. How many terms do we have? 1, 2, 3, 4. Terms are what you add or subtract. Each of the terms could be listed by separation of comma. I would list these terms as negative 3x to the 8th, comma, negative 6x squared, comma, 2x, comma, negative 3. What's the degree? Well, the degree is the term that has the highest exponent on a variable. So variable, variable, variable terms, highest exponent is 8. So I would say the degree of this polynomial is 8. What's the lead coefficient for my example? Well, my eyes have to land on the term that has the highest exponent, so it's here, this first term, so the lead coefficient would be negative 3. If you're asked what's the lead term, that would be the entire term itself, not just the number negative 3, but negative 3x to the 8th. This example is already written in standard form, so we don't have to rearrange it. You can notice that the exponents decrease from greatest to least of any variable terms that we have, terms that have letters in them. 8, 2, and 1, that's in a descending order numerically, so we didn't have to put that example in standard form. All right, it's good to know the structure and the breakdown and the language that's associated, because when we start to talk about polynomials, if I say, what's the second term, I want you to be able to know and what to go in and grab and say, that's the second term. All right, let's move on. Adding and subtracting polynomials. Polynomials are added and subtracting by combining like terms, terms with the same variables, same letters, raised to the same power. So our variables, our letters, have to have the same exponent before we can collect them or combine them or add or subtract the coefficients on those terms. All right, before we get to a subtraction example, because that's what I have here in example 2, okay, notice the grouping symbol. This set of parentheses groups this whole polynomial together. So I want to take this polynomial and I want to subtract this whole polynomial right here. And they are, each of these groups are polynomials. They satisfy the requirement given above. Before we do the subtraction one, I want to do an addition problem. And you don't have this on your notes. And if you want to write this on a separate sheet of paper, fine. Or if you just want to observe, Okay, so I'm going to say let's consider adding polynomials first. So let me move this over here. Might have to zoom in a little bit. Okay, you might notice that what I did was I actually wrote down that same problem in example 2, but instead of putting a subtraction sign, I put a plus sign, an addition sign. So let's go ahead and do an addition problem first, and then we'll use the same problem to do a subtraction problem. Our answers should be different. All right, when I add these two polynomials and they're grouped with parentheses, I first look at that I'm adding. Well, you can think of an understood 1 in front of this parentheses right here, and then this becomes a situation where I might have to multiply that positive 1 inside this parenthesis. Well, multiplying by positive 1 is not going to change the value of anything, so it's really not necessary to put that understood 1 here and distribute a positive 1 in to multiply by each of those terms, because it's not going to change anything here. So for this particular example, what I'm going to do is I'm just going to remove the parentheses in the upfront problem. Those parentheses serve no purpose. And then over here, I know that when I add, that these parentheses serve no purpose either. I'm just going to be multiplying every term in this second set of parentheses by a positive 1, which won't change anything. So really what you can do is just drop the parentheses and go plus, and then rewrite all the terms again. So in this particular example, parentheses had no effect. I can remove them and it won't change anything. All right, first thing I do is I look for terms that have the same variable and the same exponent. So I see that I have an x cubed and I have an x cubed here. To combine like terms, I look at the coefficients and I say, okay, well, these are the same kinds of terms. So if I have 13x cubes and then negative 7x cubes, let me combine 13 and minus 7. That results in 6. So that means I really have a total of 6x cubed terms. So positive 13 and negative 7 combined to positive 6. So I have 6x cubed terms. Then I look for the square terms. So I notice I have a square term here and a square term here. So I have negative 9 of the x squared terms and positive 2 of the x squared terms. Well, let's combine negative 9 and 2, and that makes minus 7, negative 7. So that means I have negative 7 x squared terms when I combine them. Now I'm going to look at the linear terms. So I say linear, the reason I'm saying that is because the understood exponents are 1, and linear terms have exponents of 1. So I have negative 7x and negative 5x. So I've got negative 7 of these x's and negative 5 more of these x's. So negative 7 and negative 5 combine to negative 12x. I keep the same exponent of 1. That leaves just these constant numbers right here. And so 1 plus 9 is 10. Let's go back, take the same problem, but now observe that we're subtracting. All right, so in example 2, we're subtracting. This subtraction sign is very critical right here. I don't need the parentheses up front. They serve no purpose, so I'm going to go ahead and remove them. However, I can't just remove these parentheses right here and have a minus and then just write down exactly what I see within these parentheses, because mathematically what's happening here is it's saying I want to subtract each and every one of these individual terms. I need to put a subtraction sign in front of each and every one of these 4 terms here in this second set of parentheses. Another way to think about it is, if you don't want to just think about subtracting each of them individually, mathematically what you're doing is you're going to write in this understood 1 that's in front of this parenthesis, because there's not a number, so it has to be understood to be 1. Think of this subtraction 1 as a negative 1 that you're actually going to multiply inside distribute, using the distributive property. You're going to multiply negative 1 by all these terms. Well, multiplying by negative 1 is going to change the signs, the positive negative signs of all of these terms. Multiplying by positive 1 wouldn't change any signs. but multiplying by -1 will. So just one at a time, and I encourage you to write these arrows. It just keeps me, it helps me, it prevents me from missing something. So -1 times -7 becomes +7. So I'm going to change this subtraction that I put down here to the first multiplication gives me 7, and then I have x cubed. Only multiplying the numbers. -1 times +2 is -2, and I keep the x squared. Negative times negative is positive 5x, and the last multiplication gives -9. This step isn't something we did on the addition of polynomial problems because you're just adding, but subtraction has a whole different effect on a polynomial or anything. Now we're at the point where we can just collect or combine like terms. So I see I have x cubed here and x cubed here. I have 13 of them here and I have 7 here. So that's going to give me 20 x cubed terms. Looking at the x squared terms, that's what my eyes focus on. I look at the coefficients, -9 and -2 combined to -11, x squared. I kind of lightly cross them off just in case I make a mistake and it's not completely wiped out. I have, I think this is a -7x and a +5x. So those combined, because they have the variables x have the same exponent, -7 and 5 make -2x. Now notice that 1 and then -9 becomes -8. And of course you have a scientific calculator if you want to just do all that number crunching on the calculator to help you combine like terms when you're working with the coefficients and trying to put them together. Okay, let's look at multiplying polynomials. So we just looked at adding and subtracting. Okay, now we're going to look at multiplying. All right, it says using the distributive property. Here's the problem. Well, what does it mean when it says use the distributive property? Well, that means take the factor that's in front, 2x squared, multiply it into each of the terms that are contained within this group. So I'm going to show these arrows. I think you should too. It just kind of keeps you on track. I'm going to multiply 2x cubed by x cubed, by 3x, and by 4. So now we have to kind of, in our brain, change our rules now. Remember, we're multiplying and we have properties of exponents also that are involved here. So what's 2x squared times x cubed? If you need to go off to the side, 2x squared times x cubed, and write it out, great. All right, the way I tackle this and handle this is I first look at the coefficients, the numbers, the real numbers in front of the factors, the variable factors. Well, this is 2, and this understood coefficient is 1, so 2 times 1 is 2. So I write down 2. Everything's being multiplied. 2 times what? Well, now let's focus our attention on the variables. X squared times x cubed. We're multiplying with the same base from our previous lesson, so that means we have x, and we're going to not multiply 2 and 3, but we're going to add them. So 2 plus 3 is 5. Let's move on now and go back to 2x squared. We have to multiply it by 3x. So 2 times 3 is 6, positive 6. If it was negative, I would record a subtraction. 2 times 3 is 6. X squared times x to the first. Well, let's add the exponents since we have the same variable x. 2 plus 1 is 3. And then the last product. Product is what you do when you multiply. Well, this is just 4, no variables, so just multiply 4 times 2, and we're going to get 8. And we have the x squared still that's part of the multiplication process. All right, multiplying a binomial product. Okay, so the language here, we're going to multiply. Binomial means 2 terms. And you read that back up there at the top. Binomial means 2 terms. So multiplying a binomial product. So notice that we're multiplying, but we have 2 groups of parentheses here. And within each of the sets of parentheses, we have 2 terms. So in this first set of parentheses, we have the terms 7x and -5. In the second parentheses, second grouping, we have the terms 4x and -3. So how do we multiply these two together when each of these parentheses have a binomial, unlike up here where 2x squared was a monomial. It's one term multiplied by a trinomial, or 3 terms. Well, some might say let's use the FOIL method, and all the FOIL method is just a method of keeping track of all the products that we have to find. So we're really distributing, but in an organized way. So FOIL method, FOIL, F stands for the first terms of each of the 2 parentheses. So I'm going to do some arrows, and I don't try and think about FOIL too much. I just know that when this problem's presented to me, I know the strategy of having to multiply 2 binomials. So I'm going to multiply 7x, this first term, times 4x, this first term. That's the first terms. Outside terms. Okay, what are the outside terms in my problem? Well, the outside terms, if you forget about the parentheses, the 2 outside terms would be the 7x and the -3. So notice what you just did here. You're taking 7x, this first term, and you're multiplying it by every term that's part of the second parentheses. All right, we got the F and the O. Let's get the I. So what are inside terms? Well, if you forget about the parentheses, these 2 terms are the inside terms. So just to kind of be a better visual, I'm going to come down here. I'm going to take -5 now and multiply it by 4x. Then the last terms, well, that would be the last terms of the 2 individual parentheses. So that's -5 being multiplied into -3. So if you don't think about this so much, think about what we're doing here. We're taking the first term of the first parentheses, and we're multiplying 7x into each of these 2 terms, but then we have to come back and grab the other term that's in the first set of parentheses, -5, and multiply it also into the 2 terms that are part of the second parentheses. So that's the FOIL method. You can remember FOIL, or you can just think about methodically and with organization, taking each term of the first parenthesis and multiplying it into every term of the second parentheses. All right, let's do the multiplication. So 7x times 4x gives 28x. Now remember, it's x squared because you're multiplying x to the first times x to the first. So you add those 2 exponents. 7x times -3, well, that's -21, and I just keep the x. Now let's look at my other 2 arrows here. -5 times 4x, that's -20x. And the last 2 numbers that we're going to multiply, the last product we're going to get is +15. And before we leave this problem, let's see if there's any combining that we can do. Well, I see just one x squared term, so 28x squared. However, I do see that those are like terms because the variable x each has an exponent of 1. So let's combine these coefficients, and that's going to be -41x. Not x squared, because I'm not multiplying. I'm just putting these 2 together with these 2 numbers. And then the +15. Okay. So on the back, we have a couple more practice problems with multiplying polynomials. If you're comfortable with what we're doing, well then just pause the video, complete the next 2 problems, and then come back and kind of fast forward the video and see where the answers are and just check your work. Self-assessing is always good. That's kind of one of my things. I always think it's good to kind of self-assess. You know, do what you can on your own first and then come back and see how you did. So what if you make a mistake? Correct it. All right, so example 5. I know that I'm going to distribute the x into both of the terms of the second parenthesis, and then I'm going to come back. I need to take the second term of the first parenthesis and multiply it into every term in the second parenthesis. So the arrows just kind of keep me on point. Let's do the first product then. So what does x times 3x look like? Well, there's a 1 in front here. It's understood. So that's just 3. And x times x gives us x squared. The second product here, well, I see that I'm going to have a 1 times a -5. So I think I'm going to have -5. How do we handle x times y? Well, we just write it, x times y. Let's move to the 4y's distribution into the last 2 terms here. So let's look at multiplying these 2 terms. So 4 times 3, that'd be +12. You could write yx, but it's kind of common practice to write the variable factors, the letter factors in alphabetical order. So I'll put that as xy. And this last product, 4 times negative 5 is negative 20. Y times another y would give us y squared. So before we leave the problem, is there some more work we can do? Well, when I look at these two middle terms here, I'm kind of studying the variable part of these terms. Well, they're exactly the same variables, and each variable has the same exponent. That means I can combine the two coefficients and collapse this into one term. Negative 5 and positive 12 give positive 7, xy terms, minus 20y squared. Okay, I think we'll continue and finish example 6, and then we'll stop there, and in the next video we'll finish the special patterns. If you're comfortable with the special patterns and you don't need me, then just attempt them on your own, and then in the second video you can just check the answers and see how you did. Make any adjustments if need be. All right, now notice we're going to multiply a binomial and a trinomial. So this first parenthesis is our binomial because we have 2 terms, and in the second parenthesis we have 3 terms, so that's our trinomial. So we can't use the FOIL method because that's only associated with a binomial times a binomial. But we don't need to worry about that. We have a strategy that works for multiplying any type of polynomial together. We're just going to take the first term of the binomial and multiply it by all 3 terms in the trinomial. Then we're going to come back. We haven't used the 2 yet. It needs to be multiplied by all 3 terms of the trinomial. So notice that we're going to have 6 products, and then we'll take a last look at it and see if there's any combination we can do. So x times x cubed, it's going to be x to the 4th. X times 3x is 3x squared. X times 4 is 4x. Now let's look at these last few products. So 2 times x cubed is 2x cubed. 2 times 3x, multiply the 2 and the 3, get 6 and keep the x. And 2 times 4 is 8. This is a correct answer. It's just not all the way done if there's some combinations that you can do, combining you can do. All right, x to the 4th, I can't collect it. There's not another x variable that has an exponent of 4, so that's done. I'm going to write this in standard form, so even though 3x squared comes next, I'm going to scan and see, oh, 3 is higher than 2, so I'm going to put 2x cubed next. Then I have 3x squared. It's the only term having that exponent. So then I see I have 10x when I combine those 2 terms, and then plus 8. Oops. All right, so in this polynomial, we have 1, 2, 3, 4, 5 terms. Okay. All right, and because I have just a little bit in time left in this video, I wanted to show you something very at the very beginning. When we were looking at examples of what polynomials were, I meant to show you what are some non-examples. So before I end here, I wanted to kind of share with you some non-examples of polynomials. So just kind of take a quick look at those and see if you know why, based on the definition of a polynomial. Think about why in each of these 3 examples, these are not polynomials. So for this first problem right here, okay, I want to look at the variables and I want to look at their exponents. They have to be whole numbers. And right here, 1/2 is not a whole number. So this is what contributes to this problem right here, this expression not being a polynomial, because that exponent is not a whole number. 1/2 is not a whole number. Now, notice that I put a 1/2 here as a number, a coefficient in front of x cubed. Well, the definition of polynomial says the coefficients just have to be real numbers. Well, 1/2 is a real number. There's no I with it. So the reason this is not a polynomial is it doesn't have anything to do with this 1/2 right here in this term. It has everything to do with that exponent not being a whole number. All right, look at example 2. That's not a polynomial. So when I look at this term right here, that exponent is a whole number. That coefficient looks kind of weird and wonky, but pi is actually a real number. It's irrational, it's not rational, but remember that rational and irrational numbers are all part of the real numbers. So pi is a real number, so this term is okay. It's just that I see this lowercase I, and typically that's not a variable. It represents the imaginary numbers. So when I see I, and that's not a real coefficient. So for example, this is the coefficient on the variable y. This coefficient is not a real number. That's what contributes to this expression not being a polynomial. And this is 9z, and minus 9z is okay. 9 is a real number, and z has an understood exponent of the whole number 1, so we're good. So this is the term that causes this expression not to be a polynomial. This is the term that causes that expression not to be a polynomial. Okay, see what you think about the third example. This is a real number constant. A constant is usually a number just by itself, no variables. We don't call it a coefficient, it's a constant. So this is a real number constant, that's good. Everything else looks fine here. It's that exponent. That's an integer exponent. It's a -4. That's not a whole number. So what contributes to this being a non-example of a polynomial is this negative exponent right here. All right, so in the next video, we'll continue looking at special patterns.